Hello everyone. In this session, let me continue the theorem on measurable integration. Here I have a statement. Let n is equal to 1 to infinity be any infinitely decreasing sequence of measurable sets in R with m of ei. Remember, I don't have star here. And when you have star, it represents outer measure. But it is, as I already told you in the previous session, it represents a restriction on outer measure. That is, m of ei is less than infinity for at least one I. Then I have to prove that limit n tending to infinity, m of en is equal to m of intersection n is equal to 1 to infinity en. Meaning is, when you are going to take limit on m into en, you just remove the limit and I can apply intersection in between m and en. Fine. So before getting to the theorem, let me revise the concept that you have already learnt in real analysis. So suppose if I have a sequence, say en, and a sequence en is decreasing, infinitely decreasing sequence, then en plus 1 is less than or equal to en. So you have already learnt about limit supremum, limit infimum, and infinitely decreasing sequence, monotonic sequence, and infinitely increasing sequence. All those things are basic. If you understand real analysis very well, measurement integration will be easy. See here, suppose if I have en is infinitely decreasing sequence, then I can write en plus 1 is less than or equal to en. Suppose en is monotonically or infinitely increasing sequence, then en is less than or equal to en plus 1. So throughout this, you have to remember this concept. Clear? Now, let me continue with the theorem. Here, en are infinitely decreasing sequence. Fine. So given data is, it is infinitely decreasing sequence, and we have to prove this statement is true. So also given that it is measurable set, en is infinitely decreasing sequence of measurable set. So I can write, given en is measurable, also it is infinitely decreasing sequence, right? So if it is infinitely decreasing sequence, I can clearly write that en plus 1 is less than or equal to en. Just now I have told you, see here, if it is in decreasing sequence, I can write en plus 1 is less than or equal to en. So that is what I have written now. So now let me assume, I'm going to skip all the statements and I'll forward the notes. Let me assume a set E is equal to en, or else I can say set E is equal to en, n is equal to 1 to infinity, and let me set fn is equal to en minus en plus 1. In the sense, I have taken a difference of these two sets as fn, that is en plus 1 minus en, and E, I have already told you, it is intersection of all the open sets en. Fine. Now, since fn is measurable, as I already proved in the theorem, that if we express E as intersection of all the open sets, and I have taken fn as in terms of en, so that implies that f is measurable and they are mutually disjoint. As per the second theorem, hope so, it is mutually disjoint. As I express E in terms of intersection of all the ens, and further fn is in terms of ei, so I can say f is also a mutually disjoint set. Now let me consider en minus e. Fine. Now let us consider en minus e as union of n is equal to n to infinity fn. Fine. Now I have considered this. Let me take measure on both sides. Measure of en minus e is equal to measure of union n is equal to n to infinity fn. Fine. Since I am taking measure inside, as per the property of outer measure, countable additive over disjoint measurable set. I have already told you, proved this theorem, m is countable additive. As per that property, when you are going to take union outside, you are going to get summation. Union will change us to summation and take m inside. This theorem I have already proved in the previous session. Now let me write this as what I have assumed. It is infinity, right? What I have assumed for fn as en minus en plus 1. I have substituted the value. Now measure, I'm going to split it, so you are going to get m of en minus m of en plus 1. LHS as it is, m of en minus e. Fine. Now what I'm going to do is, remember when you have I'm sorry, I forgot to tell you, remember when you have like summation, n is equal to n to infinity, I can write the same as like limit n tends to infinity, I is equal to n to n. I have changed the suffix n to I. Remember, as n tending to infinity, the small n changes to infinity, so you will get back the same. So I can write the summation value n is equal to n to infinity as limit n tending to infinity. I have changed this suffix n to I such that I is equal to n to small n. Whereas small n tending, as limit n tends to infinity goes to, this value will become I is equal to n tending to infinity, in the sense infinity. So I have obtained the same summation value. So I can rewrite this as limit n tending to infinity, I is equal to n to n. So I'm going to apply the same concept now. I can rewrite the summation as limit n tending to infinity. As soon as I change this suffix n, I can change this also. I is equal to n to n. Now as n tending to infinity, you will get back the same summation. Fine. Now what I'm going to do is I'll put for the first time, let me keep as it is, en m of e n plus 1. Now I'm going to remove the summation value. So the minute when you remove summation value, you have to substitute the values of summation. That is limit n tending to infinity, you keep as it is. Now put n is equal to capital N. So you will get m of en first value minus second value. For the second term, you will get m of capital N plus 1. Now substitute n is equal to n plus 1. See here, summation values ranging from n to infinity. So first value is n, second value n plus 1, n plus 2, it goes on. So first value I have substituted as capital N. So I have replaced, I have changed this suffix n to I, right? So I have to change here also. So I have substituted I is equal to capital N for the first time. So I have obtained this whole term as this. Now I am going to substitute second term, that is I is equal to n plus 1. You will get plus m of e n plus 1 minus m of n plus 1 will give us n plus 2. So when you continue this process, you will get last term m of en. It ranges up to small n. So it will become small n minus m of e n plus 1. So this is what you're going to get. Now you can note that all the successive terms get cancelled. When you go on expanding these terms, all the successive terms get cancelled, previous terms. So only remaining term will be first and last. So let me write LHS as it is. M of En minus E is equal to limit n tending to infinity, m of En minus m of e small n plus 1. Remember, here first value is capital N, last value is small n. Why? Because summation ending value is n. Clear? Now I am going to apply the limit inside. So when you do that, you will get, let me continue here. See here, m of e n minus e will be equal to, I am going to split this. See here, when you apply summation inside, limit inside, since first term is independent of small n, right? So no need to apply it for the first term. So first term let me write as it is. Why? Because it is independent of small n. Now I can apply this to second term, minus limit n tending to infinity m into e n plus 1. Clear? Now I am going to split this. M of en minus me is equal to m of en minus limit n tending to infinity m of en plus 1. Clear? Now m of en get cancels on both sides. So what you are going to get is, at the same time I am going to cancel negative. So let me write one more step. Minus me is equal to minus limit n tending to infinity m of en plus 1. So minus minus get cancelled. What you are going to get is me is equal to limit n tending to infinity m of en plus 1. Since this condition is true for all n plus 1 sets, in the sense it will be true for all n sets also. So I can write the same as m of e is equal to limit n tending to infinity m of en. Fine. Why? Because it is true for all n plus 1 open sets. So it is always true for n. Something like, suppose if you have three numbers in a set, if it is true for third number, it will be true for first number also. Why? Because as the set contains same number of elements with the same property. I am repeating once again, if some property satisfied for third element, it will be true for all the elements in a set. Why? Because as the set contains elements with same property. So I can write en plus 1 as en. Clear? Now I can rewrite the same as, let me rewrite this. Why? Because I have assumed E as, see here, I have assumed E as intersection of n is equal to 1 to infinity En. So I'll replace E with intersection of, by this I can write E can be written as n is equal to 1 to infinity En is equal to right hand side as it is, limit n tending to infinity measure of En. So that is what we have to prove is. See here. I'm repeating once again. See here in the statement what it is given, it is infinitely decreasing sequence. So if it is infinitely decreasing, I can write like this. And I have already proved in the second theorem, if E can be expressed as countable intersection of all the open sets, so it will be measurable and also mutually disjoint set. Since F is expressed in terms of En, so Fn is also measurable and mutually disjoint. Now let me consider this expression, and I have taken measure on both sides. Fine. So when you take measure on both sides, I have already proved the countable subadditive property of measure, that is restriction on measure. I can take summation, I can replace union with summation, and I can take measure inside. So Fn I have replaced with the obtained expression. So I have obtained this. Now what I am going to do is, I have changed the summation suffix. I have changed n from I, as I already told you, as per the property I can write. So as n tending to infinity, I have expanded the term. So I left with this. Now the next step, I split this term with applying the measure. So since this first term is independent of n, small n, so I am not going to apply limit for this. I can apply limit for the second term. Now after simplification, I have obtained this. Since this expression is true for all n plus 1 number of sets, so it will be true for all n sets. So I can write this expression. Since I have assumed E as intersection of all En, so I have replaced it. I have obtained the theorem. Hence the proof. Hope it is clear. Now let me see the next theorem. This theorem is similar to the previous one. See here, in place of intersection we have union. That's all. When you're going to take union, again you are going to get the same. When you're going to take intersection also, you're going to get the same. So rest of the things will be as it is, but where it is for increasing. Remember, for infinitely increasing sequence you will get union. For infinitely decreasing sequence you are going to get intersection. That's all. Proof is a bit similar but not exactly, since in the question itself it is clearly mentioned that the sequence is infinitely increasing sequence. So as I already told you at the beginning of the session, you just revise it. So when the sequence is monotonically increasing, I can write En is less than or equal to En plus 1 as per the monotonically increasing definition. Fine. Now let me set E is equal to union of n is equal to 1 to infinity En. Fine. I'll show you the previous theorem so that you will get an idea. See, theorem is quite similar, just for your reference, that is in order to remember easily. So E is intersection here in this theorem, but in this theorem E is union of all the open sets. And let me set Fn as, remember this, only this term is changing. Fn instead of F1 I'll take Fi as Ei plus 1 minus Ei. Since it is increasing, first you have to take highest term. Since it is decreasing, you have to take lowest term followed by the highest term. It's just a hint for you. You have to remember this. Fine. Next, since Fn's are also the same procedure, you have to write Fn's here. En's are all what we say measurable and disjoint sets. Then Fi is also measurable and disjoint. Whatever the definition I have written, write the same here also. Fine. Now let me consider E minus E1. But here I have considered En minus E. Here E minus E1 as union of n is equal to 1 to infinity Fn. Now take measure on both sides. You will get measure of E minus E1 is equal to, rest of the definition I will forward in the notes. In the group. You just copy it. Just procedure I am explaining. I have taken measure on both sides for the above step. Now I am going to operate the what we say countable additive property. Countable, M is countable subadditive property. I have proved in the previous session. Please open that video and you can go through that. As per that, when you are going to take union outside, union will become summation. So I can write summation n is equal to 1 to infinity. I can take measure inside. So M of Fn. Fine. Since you have summation here, as I already told you in the previous theorem that when you're going to change summation from n is equal to 1 to infinity, I can rewrite this as limit n tending to infinity. I have to change the suffix from n to I. So n tending to infinity will give us same summation. So I can write this as limit n tending to infinity I is equal to 1 to n. M of, I can change this suffix as well, Fi. Clear? Again, let me rewrite this. Limit n tending to infinity, summation I is equal to 1 to n. M of fi can be written as ei plus 1 minus ei. Clear? Now, let me remove this summation. So, limit will be as it is. For the first time, I is equal to 1. So, you will get m of 2 minus m of 1, e1. Plus m is equal to 2 will give us m of 3 minus m of e2. So it continues. For the last term it is n, right? So you will get m of e of n plus 1 minus m of en for the last term. Fine. So you can notice that m of e2 get cancelled with m of e2, but m of e1 will never cancel. Why? Because after m of e2 you will get m of e4 minus m of e3, but you are not going to get m of e1. So in somewhere you are going to get m of e3. So all the terms get cancelled except m of e1 and m of en plus 1. Fine. So remaining term I am going to write here, limit n tending to infinity minus m of e1 plus m of en plus 1, or else I can write this as, let me write LHS, m of e minus e1 is equal to limit n tending to infinity m of en plus 1 minus m of e1. Clear? Let me split the limit. So since this term contain n, so I can split this n tending to infinity m of en plus 1. I cannot apply limit for this. Why? Because it is independent of n, so I can write this as m of e1. Now I can split this m of e minus m of e1. Again m of e1 minus m of e1 get cancels on both sides. Left with m of e is equal to limit n tending to infinity m of en plus 1. So as I already told you in the previous theorem, if it is true for all n plus 1, it is also true for all n sets. Why? Because in a set, if it is holds good for one set, as a set contains an elements of its same property, it will be holds good for all the sets. So I can write m of e is equal to limit n tending to infinity measure of en. Now in place of e, what we assumed is union of en. So I can write this as m of union n is equal to 1 to infinity en is equal to limit n tending to infinity m of en. So this is what we have to prove. Proof both the theorems is simple, but you have to remember where we have to change. That's all. For monotonical increasing, remember you are going to get union. For monotonic decreasing, you are going to get intersection. Rest of the proof is same. So it is also important. I think it is asked in one of the year. Hope so. It is 2017. I don't remember exactly, but please go through this. Now let me look at the next theorem. Let en be the infinite increasing sequence of sets. Either it may be measurable or non-measurable in a set of real numbers. Then we have to prove that m star of union n is equal to 1 to infinity, en is equal to limit n tends to infinity, m star of en. This is what we have to prove. Now coming to the proof. So go to the statement. In the statement what it is given, the sequence is infinitely increasing sequence. So as I earlier said clearly that when a sequence is increasing, we can say, since given all those statement I'm going to skip, I'll just write the proof part. So given that since the sequence is increasing, infinitely increasing, so I can write en is subset of en plus 1. Just now I have said. So if that was the case, remember for any infinitely increasing sequence, there exists G delta set. So as I said, explained in the previous session, G delta set is none other than, it is an intersection of all open sets, right? G delta set is also defined as, it is an intersection of all open sets Gi. So there, if for an infinitely increasing sequence, there exists a G delta set in such a way that all the EIs will be in the open sets. In the sense, whatever the sequence exists in this particular set, measurable or non-measurable set, EIs will be containing in Gi, and also measure of Gi, this measure of Gi will be equal to measure of Ei. Clear? Measure of Gi will be equal to measure of Ei. Clear? Now let me denote Fn as G delta set. As per the definition of G delta set, it is intersection of all the open sets. So let me denote that G delta set by Fn. Moreover, as per the theorem that we have already proved, all the D delta sets are measurable, right? all G delta sets are measurable. So as per that theorem, I can say Fn is also measurable. Fn is also measurable. Clear? Now, just now I have proved you one theorem, right? So if a sequence is infinitely increasing, see here, if a sequence En is infinitely increasing, then I can write this statement. Fine. So let me write this statement. Since the sequence is increasing, that is m of union n is equal to 1 to infinity, En is equal to limit n tending to infinity, m of En. Since the sequence is infinitely increasing sequence, so as per the previous theorem, I can write this statement. Clear? Now we can clearly write, if you are going to take any open set, say Ei, that will be exactly contained in the next set, right? Ei plus 1. Just the succeeding set will be containing the same set Ei. Something like if I have n plus 1 number of elements, it contains n element as well, right? Previous term. So I can write Ei is contained in Ei plus 1. Now, in the same sense, as per, let me take this as condition 2. As per the assumed condition 2, I can write Ei is also contained in Gi. Fine? As per the given condition 2, I have just reversed the condition and let me change suffix I by n. So En is some particular n. Since Ei is contained in Gi, I can write some En is also contained in Gi. Clear? This implies that I can write En is contained in set of all these open sets. If it is true for one set, we can take it for a group of set. I is equal to 1 to infinity Gi. Clear? Now what I have assumed is collection of all the open sets, that is G delta set by Fn. So I can replace it with Fn. That will implies En is subset of Fn, or En is contained in Fn for each n. Clear? This is from the previous theorem, and this is obvious since Ei is contained in the succeeding term, that is Ei plus 1. This is from the equation 2, that is Ei is contained in Gi. I can rewrite this as En is contained in Gi for some n. Now Gi I have assumed as Fn, so I can replace this with Fn. By that I can write En is contained in Fn for each n. Now what I am going to do is, I am going to take union from n is equal to 1 to infinity on both sides. So I am going to do it for generalization case, that is for all Ens and Fns. So for the previous step, I have taken union from n is equal to 1 to infinity on both sides. Let me take this as equation 3. Fine. Now further what can I write is En is subset of Fn, right? So this statement I have rewritten. So En is subset of Fn. Further, Fn contains all the Gi's, right? In the sense open sets. All those collection of open sets will be there in Fn. That is what I have assumed. So further I can write this as Fn will be contained in some Gn's. In set Gi, Gi is open sets. So in open set there exist n number of sets, right? So let me take Fn is contained in some particular Gn sets. Fine. Now consequently let me take, if this is true, consequently I can write measure of En is subset of, when I'm going to apply measure, subset will become less than or equal to measure on restriction of Fn. Why? Because I have taken Fn as a collection of open sets, so I'm going to apply restriction here. So this result will be obvious. Fine, I have taken measure for the previous step. Now look at the equation 1. What I have assumed is measure of Gi is equal to measure of Ei. So I can replace measure of Gi with measure of En for some n. Fine. Why? Because I have assumed measure of Gi as measure of Ei. So I can replace Ei with any, since I have Gn here, in place of I have Gn, I have written m star of En. Clear? Now this equation I am going to rewrite as f of En is less than or equal to restriction measure Fn, which is less than or equal to, in place of measure of Gn, I can write m star of En. Now this says that, see here, this is something like say 2 less than or equal to a less than or equal to 2, meaning is a greater than or equal to 2 and a less than or equal to 2. So if both conditions is true, I can say a is equal to 2, something like that. So if both the inequation is true, I can write m star of, this implies that m star of En is equal to m of Fn. Clear? Now I have arrived this expression. Let me take this as, say, equation A. Fine. Now look at the equation 1. What we have obtained is measure of En is equal to measure of In, right? Let me write that. So I can write m of Fn will be equal to m star of gn. Why? Because what we have arrived is m of fn as m star of en, right? So m star of en will be equal to m star of gn. Just I have replaced this value with this. Clear? Let me take this as equation B. Say, just for the simplification purpose I have taken. Now by comparing the equations A and B, look at the equations A and B that I have arrived here. I am going to compare these two equations. With that I can write m of fn will be equal to m star of gn, that will be equal to m star of en. I can write. See here, they are one and the same. Since I can rewrite this as m star of gn is equal to m of fn, right? Since LHS or RHS are equal, we can equate LHS as well as, since both the terms are equal, from these two I can write this expression directly. Or else I can write, let me equate first and last. So I can write, or else let me consider equation E, one and the same. So m of fn is equal to m star of en. Fine. That is what equation A implies. M of fn is equal to m star of en. Now what I'm going to do is, let me apply the, what we say, theorem. Just now we have proved, no, for infinitely increasing sequence. I'm going to apply the theorem. Replace fn with n is equal to 1 to infinity fn, which is equal to limit n tending to infinity measure of fn. I can write. Right? Why? Because I have just now proved the theorem that when the sequence is infinitely increasing, union will become limit, right? So I'm going to consider applying union for fn. I'm going to take the collection of all the fn's. I'm going to apply measure on both sides so that this union will become limit. Fine. Further, what can I write is, since m of fn is equal to m star of en, so I can replace this with limit n tending to infinity m star of en. Right? Why? Because I have arrived that m of fn is equal to m star of en. So I can write this. So what I have arrived is measure of fn is equal to limit m star of en. Now let me consider equation 3. See here, what I have assumed equation 3 is, let me write it once again. Union n is equal to 1 to infinity. En is subset of union n is equal to 1 to infinity fn. Right? This is what I have assumed. Now what I'm going to do is, let me take measure on both sides. M star of union n is equal to 1 to infinity fn is less than or equal to m star of union n is equal to 1 to infinity fn. Now from this expression I can rewrite this as m star of fn as limit n tending to infinity m star of en. Right? Or else let me write this and this. Why? Because I can replace this value with this. So with this, above equation become m star of fn, it is en, right? M star of en is less than or equal to limit n tending to infinity m star of en. So let me say this as equation A. I'm just half of the proof is completed, so I'm just revising it. See here, in the given theorem it is given that sequence is infinitely increasing. So what I have written is, as per the definition of infinitely increasing sequence, en is subset of en plus 1. If that was the case, then there will exist a open set. What we say, G delta set. Collection of all the open sets is nothing but G delta set. It is already explained in the previous session. Please go through that kindly. And in such a way that all these EIs will be in the open set GI. Why? Because EI is also open set. Clear? So I can write m star of G is equal to m star of EI. Let me take this as equation 1. Now what I have assumed is collection of all the open sets, that is G delta sets intersection, right? Collection is none other than intersection, or I can say common open sets as Fn I have denoted. Now by the previous theorem, if the sequence is measurable, I can write this statement. So I have written the statement of previous theorem. Now just now I have proved now. I can write this statement directly as EI is subset of EI plus 1. EI plus 1 is greater than EI, right? Now En will be contained in GI as per the statement 2. Look at the equation 2. EI is contained in GI. So I can reverse this statement. En is contained in GI for some particular n. Fine. Now let me take all those open set, collection of open sets. So I have taken intersection. What I have assumed this intersection as Fn. So I have replaced here. Clear? Now let me equate first and last. what I did is I replaced this open set with Fn. So this is what I have obtained. Now what I did is I have taken union from n is equal to 1 to infinity on both sides, and let me take that equation as equation 3. Now I can rewrite this equation, and moreover all the Fn's are equal to collection of open set. Definitely that will be in one of the open sets. So let me take that as n. Now take measure on both sides for the above equation. You will get this. Again measure of Gn is equal to measure of Ei. From equation 1 I have replaced it and I have rewritten that. Now this statement implies that these two values are equal, and let me take that equation A. Fine. Again m star of Ei, what I have assumed is m star of Gi. As per equation 1 I can write like this. Now by comparing equation A and B, I can write the statement directly, right? Why? Because they are mutually equal, so I can write those three are equal further. Now let me consider equation A, and I am going to apply the theorem, previous theorem. See, here I have applied the previous theorem here also. There I have applied for the set En. Here I have applied for the set Fn. I have written the statement here directly. And moreover, m of Fn is, what I have proved is, limit m of Fn is equal to m star of En. So I have replaced m of Fn with m star of En. I have kept m star limit as it is. Now with this equation 3 become, let me rewrite equation 3 as it is. I am going to take measure on both sides. As per the monotonic property, subset will become less than or equal to, and again I have already arrived this expression m of union n is equal to 1 to infinity. Fn can be written as limit n tend to infinity m star of En. So I have replaced this with equation this. Now you can note that we have to prove this statement, right? So in order to prove this statement, one of the equality is obtained. Now we have to prove the reverse inequality, that is greater than or equal to we have to prove. So to prove the reverse inequality, now I can say any set En will be subset of union of all the sets Ei. Right? If you are going to take union in the sense collection of all the open sets Ei, one of the element will be definitely one of the open set will be definitely contained in the what we say subset of that collection, right? So for each n I can say. Now let me take measure on both sides. So I can write m star of En is less than or equal to m star of union I is equal to 1 to infinity Ei. Clear? Now m star of En, what I have arrived is, see here m star of En, I can write it as, or else let me take limit n tending to infinity on both sides. I am going to take limit n tending to infinity on both sides. With that I can write this equation as limit n tending to infinity m star of En. Fine, but we don't have n term here. This term is independent of n, so no need to apply limit for this. I can directly write. If you want, you can apply, and if in the next step you can remove it. Why? Because it is independent of the suffix n. So now I have obtained this equation. Let me take this as equation B. Now compare equation A and B. Both the inequalities are satisfied. So with A and B, I can write m star of union n is equal to 1 to infinity Ei is equal to limit n tending to infinity m star of Ei. So hence the proof. This is quite simple, and I have taken measure on both sides. Now I have taken limit n tending to infinity on both sides. Since this term is independent of n, so whether you are going to take limit or you are not going to take limit, it doesn't matter. Why? Because it is independent of n. So that is why I have taken limit for only left hand side. RHS is independent of n value, so I am not going to apply limit here. With this, the above equation become equation B. Now compare equation A and B. So by those two inequations, see here this term is here. In the RHS. Now in this equation, this term is in LHS. In the sense, I can rewrite this expression as greater than or equal to. You may get confusion that here also I have less than or equal to, here also I have less than or equal to. How can I equate these two? No. Why? Because this is something, let me take this as equation term A, and let me take this as term B. Now I have a term A here and term B here. Meaning is A greater than or equal to B and A less than or equal to B, one and the same. So comparing these two, I have obtained this, and that is what they have asked us to prove. Hence the theorem. Hope you understand. Continue in the next session.